Good morning, students. As I told you on Friday, I need to meet with Mr. Ramsey and Mr. Gallant this morning, so I'll be providing you with the lesson via the video this morning. If you were not here on Friday, there is a handout from Chapter 4 Radicals. There's 20 multiple choice questions that I need you to get done and passed in. And also there was a review about functions and function notation, and that's probably what you would have missed in class. So get the notes from somebody and you can have that review sheet. There's a handout today with gives you some practice with domain and range and being able to tell whether or not from a graph if it's a function. And so we're just going to review that a little bit, give you a chance to try a couple of questions, wrap up the lesson that we were working on Friday. So here I just added in another example. So Rachel Berry, for instance, you probably don't have this one in the notes I gave you on Friday. And I'm asking you to determine the domain and range for this relation. Now, I'm really curious, first of all, is this a function? So I'm going to do a little vertical line test. Here's a vertical line. As I take the vertical line and I move it to the right and then to the left, notice that it is only hitting this graph in one spot at any given time. Right, they're only connecting in one spot, therefore we say it is a function. This is the vertical line test. Now we're interested in what is the domain. And if we think about it, we have something a little different here. We have a dot, right? And that dot says it's not moving any further on that side. So it's telling me, in essence, it's not going to be going left forever. So we had done a few of these where they were going left and right forever and ever. Well, it's not going any further to the left. So there's no value at, what are we at, -6 and -7 that will ever be on that graph because the graph stops in that spot. So when I'm looking at domain, it's stopping right here, but it's going this direction forever. So when I'm looking at my domain, this is saying all the values of x need to be greater than or equal to -5. So for any value of x that is greater than -5, there will be a point on the graph. At 0, oh, there's a point on the graph. At 3, there's a corresponding point in the graph. At -3, there's a corresponding point in the graph. Okay, so that's looking at our domain. Now I'm looking at range. Notice that it's going down forever, right? Here's the maximum that we have. So they're going down from here. And although this one is stopping at this point, this one goes down forever. So we say that y has to be less than or equal to 3. And any number or value for y that is less than 3 will have a point on the graph. Notice greater than 3 at 4, there's never going to be a point on the graph. There's never a corresponding point. But at 0, when the value of y is 0, there's a point here and there's a point here. Right, so our range is y is less than or equal to 3. So we have inequalities. The next slide is going to give you 4 to try here. All right, so may have some trouble finding some numbers. All right, so on this very first one, the top left here, this is at 2. When we're looking at our circle, this value is -5. This value is 1. This value up here is 6. So these are all critical numbers that can help you. Down here, we've got a -4. And here, this value is a 3. This value is 4. This value is -5. That might be a little bit harder. And when you're done, I'm going to get you to pause it right now, actually. Do those 4 questions. Give yourself a couple of minutes, and then you can start again, and I'll have the answers on the board. Okay, so I'm hoping you're coming back and saying, okay, let's just check our answers. And we can see what the answers are. So we have the domain listed. For the very first one, the domain's all real numbers is going left and right forever. Every value of x will have a corresponding spot on that graph. But the range, it doesn't have an inequality. It's always 2. And that's a special case. So a horizontal line or a vertical line, you're going to have an equals. So here's a horizontal line that says y is equal to 2. If it was a vertical line, my domain would have x equals to a number. In the circle, I'll just erase that part because that's in the way. We're bounded left and right between 1 and -5. And we're bounded on the range between 0 and 6. Now, in the other one here in the bottom left, we see that x is greater than or equal to -4, kind of like the last one I showed you. My range is all reals because it's going up and down forever. And this funny one here on the bottom right is like the circle. It has some boundaries because of those dots. Here's some information that we need to have. So take a minute, copy down the notes. We're going to talk about what they are. We want to talk about discrete data. Okay? Discrete data is any value that varies from another value by a whole or countable units. So in other words, when we're dealing with counting numbers, our natural numbers, they're discrete. So anytime you have something in a graph that's like you're counting, it's a number of some things. It could be the number of marbles, it could be the number of candies, it could be the number of people. Right? We're not going to have 2.5 people in the room. Not in body anyway. So when we're counting them, that's called discrete data. Continuous data, any value that can be within a range. So usually this is identifiable if it's possible to have a fraction or a decimal for a value. Like if I wanted to look at time, time's continuous, right? So it's not like the clock actually stops, right? There's um, tenths of seconds, right? Hundredths of seconds. And so time is a continuum. So that's a big one, right? So if I can have a fraction or I can have a decimal or something along that line, right? We've got a point whatever. Then we're dealing with continuous data. So when we go to graph this, we need to understand, do I have discrete data? What's continuous data? And a graph that's considered a discrete graph, we would have it so that our points are not connected. So at least one set of the data points are comprised of discrete data. I can't connect the points because there's no meaning in between. So for instance, if I had the number of people and I had your heights, I'm not going to connect that data. It doesn't have any meaning, right? So how many people there are, what their height is, right? Like something like that, it doesn't have meaning to connect it. And I probably used a bad example, but like if the number of people coming in versus something else, right? And I'm counting it and I can't have half of a person. So that doesn't have meaning. That's a discrete graph. A continuous graph, my points are going to be connected because the data, I'll just pause. Okay, back on track. Continuous graph, my points are connected because the data that's represented between the range has meaning. So a lot of the times I might have time as my independent variable. And I may only be checking the time in my science experiment every 2 minutes. But at 1 minute, something's still happening. So I might connect that information with a line. So it's a kind of not so firm until we look at some examples. Okay, so we had two people, they were out dealing with owls. So in an environmental study in northern Alberta, we had Joe collect data on the number of different species of birds that he heard or he saw in a 1 hour period every 2 hours for 24 hours. And then Alice collected data on the temperature in the area at the end of each 1 hour period, and they plotted their data. So they each had a different task to do, and they were in the same spot, and we were looking at some information. We want to look at which of the two following graphs made by Joe and Alice need to be modified by connecting the data points. So I'm going to show you them, and I want to say, okay, well, which ones make sense to connect the dots, and which ones should just have the dots? And these are in your textbook, right? The beginning of chapter or section 5.5. Here's Joe's graph. And Joe is plotting time, right, versus number of species. So time here, this is my independent variable. And then we have the number of species during that time period. All right, so it looks like it was like 6 o'clock. He goes out and he's there for an hour and he's looking and hearing how many different species that he can see, and then he's recording that number. So there's 25. All right, so then at 8 o'clock, he goes out and he's recording how many species are seen or heard, and there's 20. And then he does the same thing at 10 and at 12 and at 1400 hours. So the question is, do I connect these dots? Does it make sense to connect them? So think about that. Would I connect them? Because there is time in between the 6 o'clock and 8 o'clock. If this is morning, there's time there. Should I be connecting that? Or is it because of this? The number of species. Right? I'm only going to go in and count like heads. And I know I can't have half of one. And that's not going to change. So this is an example where I'm going to keep the dots as they are. So when you graph the number of species against time, we should not have the points connected because only whole number of birds are possible. If I connected them, I'm going to be saying this, that although they read 24, it's saying like at 7 o'clock in the morning there was 25 and a half species of birds. So it makes no sense to connect the dots. So this would be discrete data, the number. Okay, now let's look at what Alice had to graph. Alice graphed time and temperature. Should these points be connected? Again, time we said is continuum, right? Although she just went and she tested at 6 o'clock in the morning, well, we also know between 6 and 8 there's 7 and there's 7:30 and there's quarter after 7, quarter to 8. So there is a continuum there. So is there a continuum with temperature? Well, temperature is one of those things that although I go out and I clock the temperature and we find that it's 7 degrees Celsius, and we go back out at 8 o'clock and we find out it's 9 degrees Celsius, it didn't just jump from 7 to 9. Right? Temperature doesn't just jump. It has to continually increase. So at some point in time, it was 6, 6.1, 6.2, 6.3, 6.4, and so on, right? Before it got to 9 degrees. So it makes more sense if we took these points and we connected the data because there is meaning between the data points. And then our graph should look like this. So just to reiterate here, graph of temperature against time should have the data points connected because both are continuous values and Both are continuous and the values between the data points have meaning. There's meaning between the data points. We connect the points. So let's look at discrete versus continuous graphs. So here are some examples. All right, so we have the number of fishing boats anchored in an inlet. Now, one of the things when we're looking at titles of graphs, this is the number of fishing boats in our title. We're dealing with our dependent value first. A lot of the times what we're going to have is our dependent versus our independent when you go to name a graph. So whenever you're ever interested in trying to find a title for a graph, start with your dependent value, your dependent variable. So the number of boats anchored in an inlet during a 24-hour time period, right? Because time then is your your independent variable. So it is your dependent versus your independent. So that's just when you're titling a graph. And so there's a hint in the title of a graph as to which is your dependent, which is your independent. But let's look at the questions. Why are the points on this graph not connected? Why? Because we're dealing with the number of boats. Number of boats can't have half a boat. Again, whenever you're looking at it and you're saying, I can't have half of something, then you know you've got discrete data. Okay, what is the independent variable? I already talked about this. So our independent variable is time. And notice that time is in the x part of our graph. Our dependent variable is the number of boats. And that's in the y part of our graph. Now it's asking to determine our domain and range. We're dealing with a set of data points. When it's discrete, you're going to take your domain and you're going to be listing the set of values. So we've got, I have to read this a little bit better, 9, 10, 11, 12. Yeah, okay, it's every hour. So we've got 9, 10, 11, 12, 13, 14, 9, 10, 11, 12, 13, 14, 15, 16. Our range, the corresponding ones, we have 25. Helps if I read that correctly. A 10, 8, 6, 6 there again. 10 is there again. 11 and 15. Okay, well, I'm not repeating the ones that are there again, right? Because we said that before. So when I have a duplicate value within that set, I only list it once. Okay, let's look at this next one. Try this one. Just pause it right here, and then it gives you a chance to look at it. Well, we have a height of tides at Port Clements, June 17th, 2009. So the height of the tide, I'm just going back to that naming again. And I'm going to skip to B where it says identify the independent and dependent variables. So the independent variable is our time. Oops, I kind of want to, let's do this. Independent variable is the time. The dependent variable, that's the height of the tide. All right, so we can look at our independent and dependent variables. Why are the points on the graph connected? Because we're dealing with continuous data. Does it make sense? Does it make sense to have meaning between those 2 points? So if I am looking at 930, 930 would be here. Does it make sense to have 930? Yeah, it makes sense to have 930. Does it make sense to say that the tide is between zero point 0.8 and 1.2? Right, so it's more than, actually it's more than 1 meter, right? So it might be like 1.12 meters. Yeah. When you think about the tide, it doesn't just jump up every half of a meter, right? You could actually go and you measure, you're going to have fine measuring tools to see that that water is going to continuously grow. So again, if you're looking at the words like continuous to explain something, you've got to connect your points. Now, if I looked at my domain and range, I have here from this point to this point and everything in between. All right, so here's my domain. When I'm looking at my domain, x is between 2 values, or my time is between 2 values. Between 9 o'clock, every value between 9 and we get 13, 14, 15, 1600 hours. So there's any values between those two because we've only gone out and we've checked at those times. We don't know the heights at other times. That's all that we've checked. And so then when I look at my range is only from this point to that point. So my range is between, and what would this be? Uh, 0.9 and 1.5 meters. And that would be what my range would be. Right, so we have to do a little bit of work. We need to actually be able to look at our graphs to see what we have. Okay, I have two here, two little scenarios. So what I'd like for you to do is to write these down, or at least a little bit of the data, and see if you can draw a sketch of these so I can look at these tomorrow. So what I have is a running elk. So an elk runs 20 meters per second. If you drew a graph of distance traveled versus time for an elk running at this speed, would the graph be discrete or continuous? Could you even do a little graph maybe and see what you'd think? Okay, what would it look like? A kangaroo. All right, a hopping kangaroo. A kangaroo can cover a horizontal distance of 13 meters in a single hop. If you drew a graph of distance traveled versus the number of hops, would the graph be discrete or continuous? All right, so again, maybe just draw a little chart. We're going to be talking about these two scenarios tomorrow. I do want to just look at the wording. If I drew a graph of distance traveled versus time, the distance traveled is the dependent variable. That's the y. And the time, that is the independent variable. Oh, that doesn't right there. Independent variable, and that is the x. So that wording kind of also gives it away as to what's independent or dependent. So here we have the distance traveled versus the number of hops. Right, so we know that the number of hops, this is the x, this is the independent variable, and the distance traveled here is the y, and that's our dependent variable. I do have some questions for you to do for homework. Okay, those should be on the board and the handout sheet that said state whether or not it's a function, give the domain and range. That's based on this part of the lesson. And as I had done on Friday, we're kind of combining two lessons together in certain spots, right? So we're moving on to the first part of section 5.6. And in 5.6, we want to know if I have a linear relationship. Not just any type of relation, not even just telling me, is this a function? I want to know, is it a linear function? Now here it's saying linear relationship, but we're going to deal with linear functions. And I guess I need to know, do you know what the word linear means? It's a special one. Linear means line. How do I know that the relationship I have is a line? Well, you can graph it, and it's a line. It might be points, but the points would make a solid line. Like you can tell that it's a straight line. But they could just be points, but that would give me a linear relationship. Another way is I have what's called a constant rate of change. And you've probably dealt with this with your science, especially in your physics. So we're going to look at these very in depth. Right? So we want to say if I graph it, it's a line, or if I have a constant rate of change. So here's an example. Now this one's taken again from the beginning of your textbook in section 5.6. The table value below shows the cost of pizza up to 5 extra toppings. So the cost that I have. Now it's interesting, remember, I remember doing this with other students and, okay, well, this is the cost per topping. Yeah, but they don't give you the cheese pizza for free. Right? So if you have the crust, the sauce, and cheese, it's still going to cost you. So that's our base price. And here we can see that our base price is $12. My question, first of all, is this a linear relationship? I bet you a couple of you are starting to raise your hands, even though I'm not here to answer. Right? So, yes, it is linear. But how do you know? And some of you are saying, oh, well, I know that the cost per item every time is the same. Isn't that a constant rate of change? Yeah. And when other of you said, well, maybe when I graph it, I have a line, then it must be linear. Well, let's look at it. We're going to look at this in a couple of different ways. The first way we're looking at it is there a rule for the pattern that relates the cost of the pizza to the number of toppings? So here you can see from the graph that yes, it is linear, and we have those points. The question is the rule for the pattern? Do you see a pattern in this function? Right? Just like our function machine. What am I doing? Can you write the equation that goes with it? That's going to help to give you how you know it's a linear relationship. All right, so the rule I see is that each topping costs me 75 cents every time. So knowing that rule, if I had 6 toppings, I know how much it was going to cost me. Okay? If I can't have negative toppings. Like if 2 toppings, I know it's $13.50. If I'm going to have 6 toppings, I know I am going to have $16.50. So I can determine even that cost. What pattern is evident in the table to signify that it's linear? In our graph, we know it's linear because this is making a line. I can even connect these points. There's my line. It doesn't make sense. It's discrete data, but you can see that it forms a line. Okay, so discrete data, so we don't connect the points. But let's look at the table because the table is going to give us some clues. And I'm going to look at the difference between these data points. So these are the differences in my independent variables. And notice the difference between these numbers every time is 1. So there's a constant difference here. When I look over here, the difference is 75 cents. Every time, the difference is 75 cents. I wrote a 57 there instead of a 75. So if I have, for everything of my independent variables going up the same amount, and then my dependent variable, every value is going up the same amount, that's a constant rate of change. And that tells me that I have a linear relationship. I kind of want to put that into a formula for you. You're going to see it. You've probably seen it before. But let's look at this, a rate of change. And if I take the differences in those y values, so this is saying I'm going to take two different y points. They could be coordinates, they could be in the table of values, and I subtract them. I take the differences in the two x values and subtract them. If it's the dependent divided by the independent, I get the rate of change. You've seen this before. I know you have. What's another way to write like the differences in the y's? Change in y, delta, right? And if you haven't seen it in your physics or your science, some of you who may be in your applied science, the 701 would have seen it. So it's delta y over delta x. Those change in values now. This still might be ringing a bell. What is it? Have you heard this before? Seen it before? I just lost what I was going to make the connection with. But slope, rise over run. All of these things represent rate of change. And we're dealing with slope. We deal with that when we're dealing with a line. And we can calculate that as rise over run. A lot of times we deal with that if we're just having like, plotted points. We're dealing with applied work. We call them rate of change. All of these things represent the same thing and they identify a line. I have another example. I'm going to take this information right through. We're going to look at different ways. If I have a table, if I have a graph, if I have ordered pairs, how do I determine if it's linear? So here is the first example that we have. It says the cost of a car rental is $60 plus $20 for every 100 kilometers that you drive. So you're going to be charged a certain price, okay, for the distance that you drive. Which is the independent variable? Hoping that you said that that is the distance that has been driven. My distance is the independent. The cost that I'm going to have will depend upon that. So then my cost is considered to be the dependent variable. Right? That's what we're looking for. So what's my independent? What's my dependent? Looking at the same thing with the table of values for a linear relation, a constant change in the independent variable results in a constant change in the dependent variable. So we're looking at, do I have that? Do the values in the independent variable go up, everyone, by the same amount? Or down by the same amount? So here the difference between them is consistently 100. Well then, in my dependent, I better have a consistent growth or consistent decline as well. So although everything in the independent goes up by 100, in the dependent everything value goes up by 20. So that's giving me what's called the rate of change. So my rate of change, delta y over delta x, the change in the y's divided by the changes in the x. And it's important to know that the y is on top, right? The y over the x. same data, but ordered pairs. And it's really more beneficial if you put your ordered pairs in numerical order. I still like to put everything into a table. I work better with the table. But what we're looking at again are the x's. Do I have a consistent change in values? So what's going on here? They're going up by 100. Each one's going up by 100. And then we look at the y's. And each of these are going up by 20. So I have a consistent rate of change. So look at my rate of change. We said, okay, well, this is delta y over delta x. It is the change in y over the change in x. So if I was to calculate this, I take consistently the same 2 points. So let's say that this is x1, y1. So that's the x coordinate of the first point, the y coordinate of the first point. And I call this one the second point. So this would be x2, y2. So I want to calculate my rate of change. I'm taking the 80, subtract 60 over 100, subtract 0, 20 over 100, which actually works out to be 0.2. I want to simplify that. So I can actually calculate the rate of change with my ordered pairs or with the table of values that I had. In a graph, my rate of change is the same thing. It's the differences in the y's over the differences in the x's. When I'm looking and reading it from a graph, I want to take 2 points, and I want to take 2 points that I can read from my graph. If I took this point, I can't really read what that is on my graph. So that's no good to me. I need to take 2 points that I can read. So let's take this point right here, and we'll take this point right there. And I want to look at the differences in this to look at my rate of change. So we'll call this point 1. We'll call this point 2. So it's the change in the y over the change in the x. And I need to read the y point for point 2 is 120. The y point for point 1 is 80. So 120 subtract 80. The x coordinate for point 2 is 300. The x coordinate for point 1 is 100. So this would be 300 minus 100. So this gives me 40 over 200, which is 0.2. So my rate of change is the same. Now, does it make sense that the graph, the table of values, the ordered pairs, that they all have the same rate of change? Yes, because it's the same question. Right, so these were just different ways to show that question. And that's looking at our rate of change. So the cost of the car rental is $60 plus $20 for every 100 kilometers driven. Our rate of change. The change in the dependent variable equal over the change in the independent variable. So we've got 20 for every 100, 0.2. That's my rate of change. Can you write an equation to represent this information? Take a minute. Jot down what you think might be the equation that you can use to represent this scenario, where the cost of the car rental is $60 plus $20 for every 100 kilometers it's driven. What would the equation be? This is what I have for the equation, where C is the cost, D is the distance that's driven. It's interesting. What do these things represent? What does C represent? The cost. What I'm looking for is it represents my dependent variable. What's point 2? Point 2, 0.20, that's my rate of change. What's the D? We said it's the distance driven. Yes, we call that the independent variable. And 60, well, that's the initial amount or the initial cost. This is a partial variation, is what our old textbook called it. I'm going to write a formula above it. Y equals mx plus b. We're going to be looking at this a lot when we just draw a line. The C equals 0.20D plus 60, that's an applied question. Y equals mx plus b, that would be a non-applied. That's just like the regular math with no context. But notice what's happening. The b on the end here, it corresponds to the 60. That's the original amount or the initial cost that's there. It's like that initial cost for the pizza. No topping, but it's still going to cost you. It's going to cost you $12 just to get the cheese pizza. That might be all that Justin McCracken wants, but it's going to cost him $12. Right? That concept. It's like a hall rental. Right? Maybe you're renting a hall and you're going to invite guests, so you have to book the hall ahead of time. It's going to cost you some money. And that might cost you so much per person if they're going to provide food. But if no one comes, you're still with the cost of the hall. So that initial cost. The X is independent, Y is dependent. So what would M relate to? M must relate to the rate of change. And when we start looking at that, we're going to also look at that as our slope. And we'll look later on, we're going to look at why we even might use the word or the letter M to denote this. All right, we're going to stop this lesson here. Homework, your domain and range sheet, page 294, 295, 8 to 13, page 308, 309, 3 to 5, 7, 9, and 12. All right. If there's any problems, you don't understand something, please come and see me. All right, have a good day.